Okay, so today we kind of start a new life, and we start talking about coding theory. We do very little bit, at least enough to introduce over the next 2 or 3 lectures the basic ideas that are at the base of cryptography. So of course, both with this first part and then with the second part, there will be see later about lattice systems, so like a lot of mathematical theory behind. And to have a full understanding, of course, it requires an in-depth course, for example, in this case in coding theory, would be nice. And there's definitely a lot more to know about coding theory than even what you can get in a dedicated course. So this is just a primer to understand actually how we use these things in cryptography, and then the gates are open to learn more about it. Okay. So the idea of coding theory comes from a completely different area, which is not secure communication, but it's about reliable communication. So it's coming from communication theory, right? And especially back in the day when coding theory was first formalized, obviously it made a lot of sense that people were communicating using telegraphs and telephone lines and things like this. And you can imagine that, of course, the vast majority of communication channels are noisy. So the first idea is that of a noisy channel over which you're communicating, right? So if you imagine that you're transmitting, say, zeros and ones, you expect every zero to be received as a zero and every one to be received as a one. But you can say that, for example, there's a small probability, obviously this should be small, like p, of incorrectly transmitting or incorrectly receiving the symbol. And this should be certainly be less than 1/2, or at least a equal 1/2, right? But you can imagine this is small, for example, I don't know, 1/100, or like very small anyway, of incorrectly transmitting a symbol, right? So it can happen that with a certain probability p, a 0 gets received as a 1, or a 1 gets received as a 0. And this is the base of what we call the binary, because we're only talking about bits at the moment, symmetric channel. And you can really picture it in this way. If you have a 0 and a 1, usually the 0 will be received as a 0, but occasionally it gets received as a 1 with probability p. So the probability of getting received as a 0 correctly is then 1 minus p, right? Mm-hmm. And vice versa, a 1 can get received as a 0 also with probability p, or with probability 1 minus p gets received as a 1. So you see it's a symmetric diagram. Okay, so obviously our messages now are not just single bits, but are strings of bits. And so as much as this probability of incorrectly transmitting is slow, if I transmit a lot of bits, it will come into play as a factor, right? Because then few of these bits, but still not 0 of them, will be transmitted incorrectly. And so what do I do, right? Because in a lot of cases, you can't just say, say that again, right? You can't send the message again. So you need a way to ensure that the message is understood correctly, even though there could be some errors. And so Shannon is kind of the father of communication theory. We already encountered him. And essentially he modeled the system as follows. Basically what you have a message source, right? And that is where your message comes from. And you can imagine that your message is like a bunch of bits, for example, U1 up to UK. And how can you make sure that this gets recovered correctly? Well, the first idea is to add some protection and to expand with some redundancy, right? So you encode, essentially you feed your message through an encoder, right? And your message gets transformed into x1, x2, xn, where n is strictly greater or equal than k. Okay, so in the best hypothesis, your length is the same as the original message, but intuitively this is not going to offer much protection, right? So ideally, you have this redundancy bigger than 0, and so your transmitted code word would be longer than the message. Okay? Then this gets fed into the channel. And this is where the noise comes from. So in the channel, what happens is that with a certain probability, some of the bits get flipped, in other words. And so what you receive is a code word y1, y2, yn, and some of these bits may be different. Then this gets fed through a decoder, and hopefully the decoder is able to recover the original U1, UK, and get it to the receiver. Okay, so there is your original message, which is like length k. This gets encoded into what we call code word, which is typically longer, depends by how much, but there is a redundancy there. And then this code word gets corrupted over the channel because there's some noise, and in the binary symmetric channel you can really imagine that you're flipping bits with a certain probability, and then this gets received at the decoder, and hopefully the decoder is able to receive not the X code word but the Y code word and still extrapolate the correct message out of it.
Right.
Okay, so this is the model that we are working on, and so of course the easiest way to do this is to how to produce code words, right? We need to create a new string, and we can set the first few symbols equal to the original symbols. So x1 is equal to u1, x2 is equal to u2, up to xk. And then this is my original message, right? And then I add a tail. Right? Rather than doing this randomly, this is like a more logical way of doing things. And so I have to then define xk plus 1 all the way up to like xn. So I have, in fact, n minus k extra symbols, right? And these are known as check symbols. And again, the idea is that I have my message, and in fact, the simplest way to do it, as we just described, is to just put it entirely in the first few positions and then add some tail. And how do I check that the message is well formed? Well, I'm going to have to require that these symbols verify some sort of condition, right? So that I know that if some error happened, then I can detect it and hopefully correct it, right? So there has to be some relation that ties all the symbols together. And so these check symbols I mean, I have n minus k of them, right? And I have to define some algebraic relation that identify them. So, for example, I can require that whatever, like x1 plus x2 plus xn is equal to 0 or something like this, right? And then I do this for a bunch of equations, for example, and then they correct me, let me identify if everything is well formed in the code word, right? So I do this over and over again. So I get a bunch of equations, first equation, then another equation, then another equation, right? And all these equations are essentially, I mean, we're talking bits, so they're going to be binary. They're going to be like 1, 1, 0, 1, 0, 1, whatever, times x1, xn, right? And that gives me the first equation.
Yeah.
And then I have another vector times that, and that gives me another equation, and so on. So what I can really think of is that I have a certain, say, matrix H, and the rows of H are exactly these kind of binary strings. And of course, this has length n, because I have to do a dot product, a vector product, right?
Yeah.
And I need n minus k of such equations because I have n minus k check symbols.
Yeah.
So I have an n minus k times n matrix here, binary, and the check is simply this times the vector of the x's, which is my code word, transposed, equal to 0.
Okay.
So then you see that the vector of the x, so code word times first row gives me 0, and then it's like the first equation. Then code word times second row, the second equation, and so on.
Right.
And all of these are equations in the x's.
Okay.
And that's how I set up these checks. And so these are check symbols. So this is usually called a check matrix, obviously. And even more interestingly, I mean, and this will make sense, we'll see later, is called a parity check matrix, in fact, because we're talking about binary.
Right.
And so really the first thing you check is the parity, whether the number of ones is even or odd.
Right.
So obviously you expect these to be a certain parity, and if a one becomes a 0, vice versa, then the whole parity is out the window, right? So that's why it's called a parity check matrix. And in fact, what you can imagine is that now I wrote just some sample equations here, right? But again, we're looking for the most logical way of doing things. So if I have to write down relations to check the redundant symbols from k plus 1 to n, it makes sense to have these symbols like analyzed one at a time. So for example, the first relation should involve only like xk plus 1. And the second relation should only involve, so the second relation means the second row of the matrix should only involve xk plus 2 and so on. And then the last row of the matrix should just involve like xn. Right? So I can look at these check symbols like one at a time, plus the first part that involves like the actual message. So I can imagine that H is really of the form like A, and then next to it, the identity matrix of dimension n minus k. Right? Because if I have, so this is like a non-zero matrix of like ones and zeros that involve like some of the message symbols, and then I have like 1, 1, 1, 1, and all zeros, right? So this means that, again, the first row will define the first check symbol as a function of all the previous ones, and then the second row will define the second check symbol as a function of all the previous ones, and so on. So it turns out that this is kind of like the most intuitive way to encode messages, and the most intuitive way of defining a parity check matrix, right? So we refer to this usually as the systematic or standard form for the parity check matrix. Okay, so we have like a non-zero matrix A, which is certain combination of the message symbols, and then like on the right you have a block which is the identity, which means you are analyzing one check symbol at a time. Okay, all of this obviously is in F2, is bits, so it's arithmetic modulo 2. Okay, so here's an example. I'm gonna put my sheet up before you tell me to. Let's take a code that is defined by this matrix here: 0, 1, 1, 1, 0, 1, and 1, 1, 0. And then here, as I promised, I have my identity. Okay. Cool. So this is an example of a parity check matrix. The barrier in the middle is just so you can recognize, but of course it's a matrix, so that's not really necessary. Okay. So this is a code where k is equal to 3. You see that you have 3 information symbols,
right?
And then n is equal to 6. So my redundancy n minus k is also 3. This means, in fact, I'm doubling the length of my message to make sure I have enough redundancy to be able to correct things, right? So that's my submatrix A, and this is my identity matrix 3 by 3. Okay. So now, how do I encode a message using this matrix? Right. I have a message U, U1, U2, U3. Right? K is 3. And I want to transform it into X, which is X1, X2, X3, X4, X5, X6. These are vectors, okay? So I should write them with like this, but just for brevity, I can imagine, because especially if they're going to be binary strings, I don't have to use the parentheses all the time. Okay? So if I have a message U, which is 3 bits, right? I can't send it to just like a random code word. It has to have some criteria, and this is why I'm saying, like, now that I've defined a matrix, the matrix entirely identifies how each vector is mapped to each corresponding code word. And of course, you have to imagine this is a unique correspondence, right? If there's 2 messages that go into the same code word, that's not a very good code. So But this is it already. So if you have a message U1, U2, U3, that has to go into a code word X1, X2, X3, then you do set the first three equal to the original ones. And then X4, X5, X6 will be determined exactly by this.
Yeah.
So you take this vector and multiply with each row. So technically you're transposing it because the matrix vector multiplication happens like this, right? So you have like X1, X2, the way down to X6. And then you generate some equations. For example, the first one, if you do this like this, you get X2 plus X3 plus X4. Right? So you get X2 plus X3 plus X4 equals 0. And then you get the second one, which is X1 plus X3 plus X5 equals 0. And then the third one is X1 plus X2 plus X6 equals 0. So you have like these three equations. You see that's n minus k. And now you see here only X4 happens, here only X5 happens, here only X6 happens. This is why we have the identity matrix here. And in this way, once we have X1, X2, X3 fixed, we only have three unknowns, right? So it's a 3x3 system. We can solve it. We can find exactly what X4, X5, and X6 are.
Yeah.
And this gives me the code word. Okay, so for example, if I do this with the message U equals 0, 1, 1, then my corresponding code words will be 0, 1, 1, because the first three symbols are the same. And then the tail, I have to solve the equation. And so I get the X4 is 0, for example, because I get 1 plus 1 plus X4.
Okay.
1 plus 1 is 0, is modulo 2.
Yep.
And then here I get X1 plus X3, so it's like 1. So to get 0, I need a 1. And similar here. So my A is 0, 1, and 1. Okay? And this is my code. And then I can do this, of course, for every possible message, right? What really matters is that the message is a string of length k. So in fact, I have 2 to the k possible messages, right? I have 0, 0, 0, 0, 0, 1, 1, 0, 0, and so on. All the binary code words, right? So all my code words would be encoding of 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. In this case, I have exactly 8 of them. Yes? This will be encoded. For example, we've seen that 0, 1, 1 goes into 0, 1, 1, 0, 1, 1. This goes into 0, 0, 0, 0, 0, 0. And this is already like a big hint. The 0 message always goes into 0 code word, right? And so on. So then this gets encoded into 0, 0, 1, 1, 1, 0. This gets encoded into 0, 1, 0, 1, 0, 1. And then you have the other code words. You have 1. What am I looking at? 1, 0, 0, 0, 1, 1. 0, 1, 1, 0, 1. And you have 4, 6, 1, 1, 0, 1, 1, 0, and 3 ones. Okay, so these are my 8 code words because it's 2 to the 3, so it's 2 to the k.
Yeah.
And this is my code. So what is the code? It's a set of code words, right? And now with this code, I'm basically embedding length 3 messages into length 6 code words, and hopefully, if a message is happening, if an error is happening, then I can detect it and correct it. And we will see later how to do this. Okay? So we will see later this is actually able to correct exactly one error. Okay? And we will see how to do this. But already using this code reduces the error probability by a lot. If my probability, remember we said that P was 1 over 100, so like 0.01. Then using this code already reduces the probability of getting an incorrect code word to something like 0.00072.
Okay.
So of course the price to pay is that we're sending 6 symbols instead of 3, and we're doubling our length. So much of coding theory essentially is find the best way, find the best codes that give you the best bang for the buck. So how can you correct as many errors as possible, right? With the least redundancy and then of course you have to take into consideration encoding difficulty and decoding difficulty and stuff. Yes.
Could you go over how you calculated x? I thought you like underlined the x4, x5, and x6, but could you go over that?
Yeah, so the x, for example, let's do the first one, right? The first symbols are x1 is equal to 0, x2 is equal to 1, x3 is equal to 1, right? So you solve the first equation, you get 0 plus 1 plus 1. Sorry, not 0, 0. So you get x2 is 1, x3 is 1, plus x4 equal to 0. Right? And 1 plus 1 is 2, model 2 is 0, is bits. So you get x4 equal to 0. And that's why x4 is 0. We just solved the first equation.
You said
x2 is 1, right?
what? So you get 1 plus 1 plus x4, and then what did you do right after that? You said 1
plus 1 is 0, right? We are using bits.
Okay,
So that's just x4 equals 0.
gotcha.
And in the other two equations, you get, for example, x1, which is 0, so you get 0 plus 1 plus x5, which gives you x5 equal 1, and then 0 plus 1 plus x6, which also gives you x6 equal 1.
Okay, got it.
So yeah, you really are just like using the equations, okay, for now. Later we will see that there is actually a better way to encode things. But the principle is that of using the parity check matrix, because it's defining a set of relations. Okay, so in fact, let's try to be a little bit more precise now.